Yes. Yes. So my screen is visible to everyone. Yeah, please confirm it.
Yes, sir.
Yeah, thank you so much. So once again, good evening to everyone. So today we have 15th class. Okay, and this one is the last online class for this semester. Okay, then next time I will take the physical class. Okay, so next Saturday I will be there. Okay, and this is the unit number fourth. So that is a dynamic modeling and simulation. So not unit number third. So unit number third we already cover. So this is your unit number fourth. Okay. So unit number, just one minute. So unit number fourth. Okay. So that is a dynamic modeling and simulation. So unit number third we already completed. That is a control of the electric drives. Okay. So in the last class we discussed the VFD, and that is the most important topic. That is a variable frequency drive of the three-phase induction motor and analysis and performance of the three-phase induction motors. Okay. So yes, from uh, the previous class I got the query, 3 to 4 queries. So there is a space vector PW method, difference between the VSI and CSI, cube law between the speed and power. Okay. So first, I will discuss these three topics. So there is a just overview of the space vector PW method, and then just discuss the difference between the VSI and CSI, and then cube law. Okay. In the last class, I said the cube law, but I was wrong that time. Okay. So I was work out on the cube law, and then finally I got the answer. Okay. And then we can start the fourth unit, that is a development of the dynamic model for the electric drive. So this is the part of the third unit. Okay. Sorry, fourth unit. So this is the third unit. Okay. And this is the fourth unit. Okay. So yet. Okay. And finally, simulation tools to check the performance of the electric drives, and finally types of the duty cycles. So today we will cover the this seventh topic. Okay. Yes. So in the last class, some student asked me regarding the space vector PWM, because most of the student not cover the space vector PWM. Maybe some student cover, but maybe the forgot. Okay. So space vector PW is nothing but one kind of the modulation technique. Okay. Space vector pulse width modulation is a modulation scheme to use to apply a given voltage vector to the three-phase electric motors. Okay, so we have to operate our inverter, correct? So we have an inverter, something like inverter, we can say three-phase inverter, correct? And here we have a DC supply. Yes. And we can connect the three-phase. We can connect three-phase motor here. Okay, and every phase is connected with this phasor. Just one minute, somebody want to join the class. Yeah. So this is the part of the motor. So we can say this is your motor. Okay. So this is your motor. And this part there is a inverter. Okay. And inverter have a six switch. So we can say S1, S2, S3, S4, S5, and S6. We have a six switch. So we have to operate this switch and we have to give the pulses for this switch, correct? So we have a different type of modulation, maybe the sinusoidal modulation, maybe the space vector modulation. So we have a random pulse width modulation. We have a many modulation techniques are there. So one of the techniques, that is a space vector PWM technique. Okay. So this is a simple technique. We have to operate every switches during the spaces, correct? So we have to divide the sector, correct? Different sector, and we have to operate the our inverter. So you can see this is the we can say the visualization of the space vector technique. So you can see this is a vector. We can say this is a vector. Vector is rotating continue to the 360 degree. So you can see this is a rotating continue to the 360 degree, correct? And we have to operate switches at different angles. So you can see we have a voltage V minus V, that is a one phase, minus W, and W, that is another phase, and U and minus U, that is another phase, correct? So we have a three phase and we have to operate every different angle, and we have a total 360 degree rotation, correct? So we have to divide the sector. So maybe this sector 1, this sector 2, sector 3, sector 4, sector 5, sector 6, sector 7. So we have to divide the sector, and then based on the sector we have to operate our inverter. Okay. So this is a simple concept of the we can say the sinusoidal or not sinusoidal space vector modulation technique. Okay. I already shared the YouTube video with Asis. If somebody want to implement the space vector modulation technique, then please let me know. Maybe otherwise, Asis, you can share that video and the link to the all the student, maybe in the your official group. Okay. So maybe the somebody want to implement that space vector modulation, then maybe they can implement in the MATLAB. Okay. Yeah. Yes. Now, second thing, there is a difference between the voltage source and the current source inverter. Okay. In the last class, we discussed the voltage source inverter. So mostly VSI people use to operate the three-phase induction. Okay. So why VSI? Why not CSI? So because there are some advantage in the VSI and some disadvantage in the CSI. But we can say 100% is not any system is advantages. Correct. So you all of you know about the inverter, correct? So inverter is what? So we have a DC supply input, and then is an inverter, and from output of the inverter there is a AC, correct? And our motor is a AC, so it is required the AC supply, correct? So we have a two type of the converter. There is a voltage source converter and current source converter, and converter is nothing but your inverter part, correct? So yes, so you can see figure number 1, there is a voltage source inverter, and figure number 2, there is your current source inverter. So both the inverter, there is a supply voltage is a DC. So you can see this is a voltage source, there is a DC supply, and for the CSI there is also DC supply. But difference is in the VSI we have to connect the capacitor in the parallel. But in the case of the CSI, we have to connect the inductor in the series. Why? We will see in the next slide, correct? Why we have to connect the capacitor in the parallel and in the case of the voltage source inverter, and why we have to connect the inductor in the case of the current source inverter. Because I hope you remember this formula V equal to L di by dt, correct? And then capacitors, in the case of the capacitor, there is a, yes, in the case of the capacitor, I equal to C dV by dt. I hope you remember this formula, that is a capacitor across voltage and voltage across inductor, inductor across voltage. Okay. So V equal to L di by dt, and current flowing in the capacitor, there is a C dV by dt. Okay. So based on this formula, we have to connect the capacitor in the inductor. Okay. And we will see in the next slide, that is a voltage source inverter and current source inverter. But just remember, in the case of the VSI, we have to connect the capacitor in the parallel across the supply voltage. In the case of the CSI, we have to connect the inductor in the series, correct? Yes. So in the VSI, input voltage is kept a constant. We have to keep the input voltage constant. So VSI is fed from the DC voltage source having the negligible, otherwise the zero impedance. So we can say yes, there is a zero impedance. So we can say the input voltage is a constant. To make the VSI, we have to connect the DC source in parallel with the large capacitor that maintain the input voltage constant. Yes, why we have to connect the capacitor? Because we have to make the constant DC link voltage. And how we can make the constant DC link voltage? By connecting large capacitor across the your supply voltage. So we can say we can keep the constant DC link voltage. So that's why we are saying in the case of the power electronics, we have to connect the capacitor bank across the DC link, across the DC supply. So we can make the constant DC link voltage, correct? In the case of the VSI, output voltage is independent of the load. Here, the waveform of the load current as well as the magnitude depend on the nature of the load impedance. Okay, so that is your output voltage waveform that is depend on your nature of the load. Okay, maybe that is an inductive load, maybe the capacitive load, or maybe the resistive load. And we know there is an inductive, capacitor, and resistive load, that is a unity power factor and lagging and leading power factor, correct? So based on the load, we can say there is a output voltage is vary. Okay. Yes, voltage source inverter is fed by the stiff DC voltage or constant DC voltage is called the voltage source inverter or voltage feed inverter. Okay. VSI, we use the power semiconductor switching device in the circuit like BJT, power MOSFET, IGBT. Yes, we have to use the controllable semiconductor switch, and whenever we can say controllable semiconductor switch means there is a firing pulses. Okay, so we can say there is a three terminal device we have to use, correct? And then we can say we have to operate the your inverter. Yes. VSI is more efficient than the CSI design, correct? This is because the VSI drive we use IGBT switching device that is a more efficiency than the GTO and the SGCT device that is a semi-gate control thyristor. Okay, in the CSI version. Okay, so ultimately we have to use the semiconductor CY devices where three terminals are available. Correct. So there is a gate, source, yeah, drain. Otherwise, gate, emitter, and collector. Correct. So based on the device, based on the semiconductor topology, we have to use the semiconductor switch. Yes. So important point of the voltage source inverter. So there are the six important point. First one is there is a input configuration. VSI typical have the DC input source, such battery or the rectifying supply the constant voltage. Correct. So there is an input configuration. Output current. The output current is controlled by the varying the inverter switching pattern or modulation technique. Okay. So that is a depend on the modulation technique we can control the output current. Okay. Output voltage control. Third point, VSI can provide the variable output voltage with fixed frequency by adjusting the pulse width modulation. We know output voltage is directly proportional to your firing pulses. And by controlling the firing pulses, we can able to control the output voltage, correct? Load type. So depend on the which type of load you can connect with your inverter. So then we can say that load, nature of the load, we can connect the your inverter. Yes. High input impedance. There is a fifth one important point. The input impedance of the VSI is typically high, which means it draw the less current from the input source. Okay, because of the high input impedance, so it will draw the less current from the input source. And short circuit protection, that is the last one. VSI may require the additionally protection circuit to prevent the damage due to short circuit to at the output. Yes, that is a protection devices. So we have to connect the every protection device for the every circuit. Correct. So see, these are the important points for the voltage source inverter. Now for the current source inverter, there is a CSI. CSI input circuit input current is kept constant. For the case of the current source inverter, we have to maintain the input current is a constant. In the case of the voltage source inverter, we have to maintain the input voltage constant. In the case of the current source inverter, we have to maintain the current constant, correct? It name suggests because current source, so we have to maintain the constant current. In the case of the voltage source, we have to maintain the inputs DC supply voltage constant, correct? CSI is fed with the adjustable current source from the DC voltage source of the high impedance. VSI can be converted into the CSI by connecting large series inductor that maintain the input current constant. Yes, suppose you have a VSI, so VSI can be converted into the CSI by connecting the large series inductor. Correct? Otherwise, circuit is same. Just we have to connect the large capacitor, otherwise large inductance. Then we can say now our circuit is a current source inverter, yeah, voltage source inverter. Correct? CSI output current is independent of the load. Hence, the magnitude of the output voltage and it is a waveform is depend on the nature of the load impedance. Okay. Yes, we have to connect the semiconductor switch. Okay, any type of semiconductor switch. That is a three-terminal semiconductor switch in the case of the CSI. Same in the case of the important point in the case of the CSI. Whatever we discuss in the case of the VSI, so same protection we have to, same important parameter we have to uh, analysis. So, what type of parameter? So, there is an input configuration. First one is an input configuration, output current, output voltage. Yes, we have to control the output current as well as the output voltage. Load type, which type of load we have to connect. Okay, there is inductive load, capacitive load, or resistive load. Yes, whenever we can say there is a motor, then always we can say there is an inductive load, correct? Okay, because we have a coil, okay, stator coil. Low input impedance, correct? The input impedance of the CSI is typically low. In the case of the your VSI, there is a high input impedance, correct? Which means draw the more current from the input source, okay? And short circuit protection, it is the same like your in the VSI, correct? Yes, so you can see this is a configuration of the VSI and CSI. So figure number 3 and figure number 4. So you can see figure number 3, that is a configuration of VSI. We have a bridge, okay? So that is a like we can say we have a like H bridge, okay? So thyristor 1, thyristor 3, thyristor 4, and thyristor 2. And we can connect our load here. And load may be your motor, yeah, maybe the any kind of load. But here you can see we can connect the large capacitor. It means there is a voltage source inverter, correct? But in the case of the suppose you connected inductor, that is large inductor, then we can say it is a your current source inverter, correct? And but semiconductor switch is the same. You can see semiconductor switch is the same. That is a three terminal switches, correct? So we have to control the our supply voltage as well as the output voltage. Yes, so this is the difference, voltage source inverter versus current source inverter. In the voltage source inverter, input voltage is kept constant, but in the current source, input current is kept constant. Yes, it name suggests that is a current source, so we have to maintain the constant current. Suppose it is a voltage source, we have to maintain the supply voltage constant. VSI feed from the DC voltage source having the small or negligible impedance, correct? But in the case of the CSI, there is a high impedance. DC source parallel with the large capacitor, yes, and VSI is converted into CSI by connecting the large series impedance. Okay. Input voltage maintain constant, the input current maintain constant and adjustable. Output voltage is independent of the load, output current is independent of the load. Correct? In the case of the VSI, output voltage is independent of the load. In the case of the CSI, output current is independent of the load. The waveform of the load current as well as the magnitude depend upon the nature of the load impedance. Correct? Magnitude of the output voltage is waveform depend upon the nature of the load impedance. Okay. So in the case of the VSI, that is a current it is a depend on the load impedance. But in the case of the CSI, that is a voltage, it is a depend on the nature of the load. Correct? Okay. VSI has a slow response than the CSI, and CSI has a fast response than the VSI. VSI requires the feedback diode because there is a voltage source inverter, but in the case of the current source inverter, CSI does not require any feedback because there is a current source inverter and that is your fast response. Okay. The commutation circuit is complicated. It is a it used the current commutation. Yes, the commutation circuit while design the VSI, we require the commutation circuit to operate the switch 1 to switch 3. Correct? So it is a complicated. But in the case of the CSI, it is a simple circuit. Correct? Because there is a no feedback diode. Correct? So that's why. Power BJT, power MOSFET, any IGBT, any semiconductor switch you can use to make the commutation circuit. Correct? But here we can use the thyristor. Okay. Yeah. So these are the major difference between the CSI and VSI. Okay. I hope now it is clear to you about the what is the difference between the CSI and VSI. Okay. Still, suppose any student have a confusion, then please let me know. Okay. Yeah.
Yes, sir.
Yes.
Sir, but one difference was their input impedance of BSI is high and CSI is low.
Can you
Uh,
just repeat?
that input impedance of BSI is high or CSI is low is something is there one difference.
Yeah. So because in the case of
How
the
how that
VSI,
happens, sir?
yeah. So this yeah. So that is second point, correct? Second point, correct? VSI is fed from the DC source having the small or negligible impedance. You are talking about this point
Uh, Earlier, sir, in that before 2 or 3 slides.
here.
Yes, sir. Here it is written high.
Mhm.
Difference it is written low.
Yes, 1 meter. Maybe the typo mistake. Yes, 1 meter. High input impedance. The input impedance of the VSI is typically high, which means there was the less current from the input source. It is correct. Low input impedance, impedance of the CSI is low, which means it is a draw the current from the input source. Yes, this is correct. Yes. So here is a typing mistake. So this one is a typing mistake. So correct one is this one. This one is correct one.
Yes, sir.
So
But how that input impedance we measure from that Thevenin's equivalent circuit,
input impedance is
that Thevenin impedance,
mhm.
which is seen by the source, either it is voltage or current source, how that becomes high for VSI and low for CSI, sir?
Yes. So because yeah. So this circuit you can see in the case of the VSI we have a capacitor, correct? And while we can say capacitor, by nature, capacitor it is a your high impedance. So suppose you can see the nature of the capacitor. So capacitor by default it is provide the high impedance. By nature, capacitor is provide the high impedance. And your inductor it is provide the low impedance. So that is the nature of the capacitor and nature of the inductance. That's why we can say, that's why we can say your CSIs provide the low input impedance because your impedance of the inductance, that is a low, but in the case of the capacitor, your impedance is a high. That's why. And that is the nature of the capacitor and inductor. Suppose you will see the nature of the capacitor and inductors, then you will get this answer. So why low and high? And that is the nature of that element. That is a we can say the uh, fundamental component of the RLC circuit. Okay, that's why. There is no specific reason about the why VSI is provide the high input impedance and why CSI is provide the low input impedance. Technical reason is because by nature capacitor and inductors provide the high and low impedance. That is a by nature, correct? So every components have a nature, correct? Got it?
Yes, sir. But while drawing that circuit, we saw if that impedance, input impedance with voltage source in series,
Mm-hmm.
but that capacitor has is placed in parallel with the
Mm-hmm.
voltage source.
Mm-hmm. So why we connect the capacitor in parallel with the voltage source and why inductor is connected series with the
That is okay. But to that maintain constant voltage, we place capacitor in
mm-hmm,
parallel.
mm-hmm,
To
mm-hmm.
maintain constant current, we place inductor in series. But to define that input impedance, if we want to draw the Thevenin equivalent circuit, then we can justify how that input impedance is high or low on the basis of circuit. So
In the
if we want,
basis of circuit.
yes,
Mm-hmm.
sir, then can we draw the equivalent circuit of VSI?
Equivalent circuit of VSI, I don't remember now how we can show the equivalent circuit of the VSI. Uh, Equivalent circuit, I not
Yes, sir.
remember now.
Here it is circuit for CSI.
Yeah. So same circuit is a here is a this is a VSI circuit, but equivalent circuit with the load we have to consider the load, correct, and then we can draw the equivalent circuit, correct.
Yes, sir. Yes, sir.
But currently I'm not remember the equivalent circuit. Then equivalent circuit you want to find out that that is the impedance, correct? So how we can find
Yes,
out the yes.
on the basis of that we can justify why it is high or that is low. I think so.
uh, I am not sure, but that input impedance, that is directly depend on the capacitor nature and inductor nature. That's why we are saying the based on the nature of the capacitor, we can say there is a high input impedance and low input impedance. Because that is a element, there is a inductor and capacitor and resistor. That nature we can define the impedance. But maybe you are right. So that is a by equivalent circuit we can justify that is the input impedance of the voltage source is a high and input impedance of the current source that is a low. Maybe you are right, but I am not sure. But I will work out on the equivalent circuit and then let you know. Is it okay?
Okay, sir. Thank you, sir.
Yeah. So I will find out. So suppose we connect maybe the any inductive load, capacitive load here, RL load, and then we can find out the Thevenin equivalent circuit, and then we can find out the impedance. Correct. So because Thevenin equivalent circuit is nothing but we can say this is a simple Thevenin equivalent circuit. So this is a VTH, and this is your RTH, and this is your load. Correct. So this is your
Yes, sir.
Thevenin
Right, sir.
equivalent circuit, and we have to find out the current. So this is IL. So we can say IL equal to VTH divided by RTH plus RL. Correct. So you are saying something like that, correct?
Yes, sir. Yes, sir.
Yeah. So I remember this Thevenin equivalent circuit, but for the equivalent circuit of the voltage source inverter and current source inverter, and then we can say it is an impedance, because impedance is nothing but Z equal to 1 by R. Correct. So we have to convert the equivalent circuit, and then we have to find out the VTH and RTH, and then we can say impedance relation. So let's see. I will work out on that, and then let's see. Then maybe we can justify that input impedance of the VSI there is a high, and the input impedance of the CSI there is a low. Okay. I will work out on that and then let you know. Okay. Yeah. Yes. Yes, cube law between the speed and power. Yeah. So in the last class, I told that cube law there is a wrong. So I am really sorry for that. So that is a relation between the speed and power of the fan or pump is called the cube law and can be built the step by step. Okay. So that is a cube law. That is your, we can say, the flow of the proportional to the speed. Correct. So suppose 10% flow, then 90% flow of the, your power. Correct. So we can say that that is a cube. So we can say yes. In the last class, I think Ashish told me. So there is a power. Correct. So maybe we can say a square, b square, sorry, b cube. Correct. So that is a cube parameter, correct? So we already know there is a fan application and pump application, correct? So there is a proportional to the cube. So we can say the torque is proportional to the speed square and power is proportional to the speed cube, correct? So we already studied this thing in the DC motor, correct? So fan application, correct? So torque is directly proportional to speed square. So we can say omega square, but power there is a proportional to the cube, correct? So this relation, in last class I think Ashish told this same relation, correct Ashish? Am I correct?
Yes, sir. Because I guess that because cube C was not capital, it was not name of any person.
So in the last class I called that C, that is a one scientist, and then we can say it is a law, correct? But I was wrong that time, and I was thinking there is a cube law is something like that because I read this cube law in the physics concept, but I think there is a something different. I hope. So yes, and then I work out on that and I got this answer. So there is a cube, that is a speed and power relation. So yes, now final correct is the torque is directly proportional to the square of the speed and power is directly proportional to the cube of the speed. Correct. So this is the final answer. Okay. In the last class you forget about yes, you skip that thing. Okay. And correct one, that is a torque is directly proportional to the square of the speed and power is directly proportional to the torque of power is directly proportional to the cube of the speed, correct? Yes. Yeah. And one more thing, Ashish, you told me there is a relation, mathematical relation, correct? But I did not find any mathematical relation for that comparison, otherwise justification. So question is, a VFD can provide the soft starting of the motor by gradually increase the frequency and voltage of the power supply from 0 to desired value. So you told me and you asked me this question, so any mathematical derivation, but I did not find any mathematical derivation from any resources. But everywhere I got this statement for this question, gradually increase the frequency. So we can increase the frequency by the power electronics converter, correct? So we have a power electronics converter. So we can increase the frequency by power electronics converter, and that is the main role of the VFD, correct? Because frequency speed that is depend on the frequency because ns equal to 120 f by p. So we can say ns is directly proportional to frequency. Number of pole is a constant, correct? So we can say only speed is 120 f. 120 is also constant, so we can say ns is directly proportional to the f. So suppose you can remove this proportionality, so we can say proportionality is nothing but 120 by p, correct? So finally, we can say gradually increase the frequency and voltage during the startup, phase minimize and induce current, and mechanical states on the motor and connected the equipment. Okay. So a role of the VFD is we have to gradually increase the frequency and the voltage. So we have to maintain the constant V by F ratio. Correct? What we are doing in the VFD, we have to maintain the constant ratio. Constant ratio of what? There is a voltage, a voltage and frequency. So we have to slowly increase the voltage as well as the frequency, and then we can say we have to operate our motor. Correct? So this result is the smoother and control acceleration of the motor and reducing the wear and tear on the mechanical component. Correct? So I got only this statement from the every book, as well as the I read the few research paper, and I also search on the net, but I got only this line. But there is a not any mathematical explanation, otherwise mathematical justification. But based on the my knowledge, I got only that ns equal to 120 F by P. So P is a constant because there is a number of pole. Once the motor is designed, then we cannot change the pole, correct? And 120 is also fixed. Okay. So we can say that speed, that is a synchronous speed, is directly proportional to frequency. In the case of the VFD, suppose you want to increase the frequency, then we have to also vary the voltage, because we have to maintain the constant V by F ratio. Suppose you increase the frequency 10%, then we have to also increase the frequency voltage, that is a 10%. Correct? But yes, mathematical explanation I did not find anywhere. Okay. Yes. Yeah. Put it. Yes, Asis. Any more confusion? Any
Yes,
more
sir.
query?
If you remember, I have also asked one question regarding power factor. Something related to power factor was there, sir.
Power factor. What was the question?
Yes, I actually forgot, sir. There was some relation how power factor improves in the previous slide. I think last slide was that.
Okay, no issue. So once the complete this class, then just message me. Okay. So that's why actually I told, because in the last class I think you asked me I think 3 to 4 question, and Madhusudan asked me 1 to 2 question. Madhusudan asked me I think the difference between the voltage source and current source, and you asked me I think 3 to 4 question, that is like cube law, as well as this statement, and third question maybe that is your power factor. I think so. Yes.
Yes, sir.
So
This is okay, but power factor was quite interesting. That
yeah. So just send me that question. Okay. So again, I will work out, because there's those question I don't know. So I hope you ask that question during the lecture, but I forget that question. So just send me that question. Okay. So again, I will work out on that question, and I will let you know the answer. Okay. So just send me that question. Okay. Just send me that question. Otherwise, again, I will forget this question and maybe the skip. Okay. So maybe now you can
okay.
message me. So otherwise, after this lecture, you can message me. Okay. Yeah. Any more confusion to any student? Any more confusion? Okay. Yes. Good. Very good. So now we can start the unit number 4th. Okay. So this is a unit number 4th. Unit number 4th. Okay. So unit number 4, that is your development of the dynamic model. Not development, that is the name of the unit, that is a dynamic model of the electric drives. Correct. So this is a just, we can say, the overview of the modeling part. Okay. So important part is the duty cycle. Okay. So development of the dynamic model of the electric drives, in the last semester already we discussed in the modeling subject why we have to model, why we have to use the simulating part, correct, for the like design of the any motor, design of the any controller, correct. So same concept is here. The development of the dynamic model for the electric drive is involving creating the mathematical representation that describe the behavior and performance of the electric drive system over the time. Correct? So main logic behind the dynamic model, otherwise the model, we can say steady state model, otherwise dynamic model. We can say we have a two condition. One is a steady state condition. Steady state condition. And another one is a dynamic condition. Correct. We have a two condition. Suppose you want to analysis the steady state as well as the dynamic condition, and whenever we can say electrical drives, then we have to always analysis steady state as well as the dynamic condition. Okay. So for the analysis of the steady state and dynamic condition, we have to work out on the mathematical model. Correct. And we know that is a voltage, current, power, and speed. Okay. So these are the five relation. That is a voltage, current, power, speed, and torque. So we have these five components, correct? So we have to do the mathematical model, and we already know that electrical machine is a complex structure because we have a rotor, we have a stator slot, rotor slot, flux, inductors, self inductance, mutual inductance. We have a many parameters, correct? And some parameter it is a constant with respect to time, but some parameter is a dynamic with respect to time, correct? So current is passing to the coil, so it will increase the temperature, so it will create the losses. It is a losses that is directly effect on the flux, and flux will change, then we can say torque will change, then we can say speed will change. So all the parameter it is dependent on the another parameter. So for the analysis, for the fine analysis, we have to use the dynamic model, otherwise the steady state model. These models are essentially for analysis, design, and control of the electric drive. And as we are the power electronics and drive student, so we have to analysis the motor, we have to design the motor, and finally we have to control the electric drives. Correct. So these are the three important things. That there is an analysis, then finally design, and then finally control. So first we have to analysis the parameter. Okay, suppose you want to design the 1 kilowatt motor, correct, otherwise 1 kilowatt drives. So first we have to analysis, and then once the analysis is done and you are satisfied with the analysis, then we have to work out on the design, how we can design these drives, correct. Once you design, then we have to really practically use these drives, correct, in the practical application. So we have to do the control. Okay, so last year I already discussed this concept. Okay, so why modeling is important. The dynamic models typically include the equation that capture the relationship between the electrical, mechanical, and control component. Yes, whenever we can say drive, otherwise machine. So machine is nothing but mechatronics, correct? So we can say it is a electromechanical, correct? So it is a relation between the electrical as well as the mechanical, correct? So it is a component of the both branch, that is the electrical as well as the mechanical component, correct. And finally there is a control component. So ultimately we have to control, correct. It is nothing but drives. Whenever we can say drives is nothing but your control of the any motion. And whenever we can say the electric drives, that means we have to control the voltage and current, correct. Yes, so major components, otherwise we can say the process step for the dynamic models. So total 11 step. Okay, so there is a define the system component. So there is a these steps are the most important. Okay, so suppose you want to modeling of the any components, any drives. Okay, so first we have to define the system components, then establish the assumption. So we have to also assume, we have to also consider the any assumption, maybe the temperature, maybe the room condition, maybe the any assumption, maybe the material permeability of the material. Okay, maybe the air permeability, maybe the flux, maybe the distance. So we have to establish the assumption. That is the second step. Third step, development of the electrical model. Okay, so first then we have to develop the electrical model, then we have to develop the mechanical, because our motor there is a both component, electrical and mechanical, correct. And then finally there is a combined electrical and the mechanical model. So we can say now our motor is ready, correct. So this 5 step. Then 6 step include the control system dynamics. Now once the motor is ready, then we have to include the control system dynamic, correct. And then after that validation and the parameter. Okay, so then validation and parameter. Okay, then non-linearity and the advanced features. Suppose your motor is the operate in the non-linear region, then what we have to do, correct. Then finally the simulation. Sensitive analysis. Sensitive analysis is means suppose suddenly your motor is in the faulty condition, then what we have to do. So we have to shut down our motor. Yeah, still we can run our motor with the 50% load cutting. Yeah, maybe the 60% load cutting. Okay, so that type of sensitive analysis, and we can say it is a fault diagnosis system. Okay, suppose suddenly fault is created in your motor, correct. So we have to shut down our system. Yeah, still we can run our system. Maybe the 50% of the load reduction, correct. And finally, we can say step number 11, that is a documentation, correct? So we have to report every condition and every step in the written proof, correct? So we can say finally we have to make one simple report on that dynamic model, correct? So these are the total 10 steps. So this documentation is the most important part, correct? Whatever we are doing, we have to make the proper note so we can not forget the any concept, correct? So that is a final step, that is a documentation. So total step is a 10 step is the most important part, and 11th, that is a documentation, correct? So documentation in the case of the maybe the physical documentation, maybe the digital documentation, but as per the time, depend on the time parameter, we have to make the documentation, correct? So maybe the today you can perform the one experiment, maybe the after 1 week you perform the second test, maybe the after 10 day you perform the third test. So maybe the you forget the reading, maybe the after the 1 month, yeah, after the 2 month. So that's why we have to note down the every parameter with time, correct? So maybe the today is the 4th March and we perform the no load test. So we have to note down the every parameter, correct? And maybe the after 10 days, yeah, maybe the after 20 days, you perform the short load test, correct? So with load and without load, okay? No load test and full load test, we can say, correct? That is simple example, correct? So this is the development of the dynamic model, okay? Yes. So what is the for the like every step I mentioned the 2 to 3 lines. So what is the meaning of the define the system component, establish assumptions? So I'm not going to detail about that step. Okay. So like define the system components. So we have to identify the key components of the electric system drives. This may be include the motor, power electronics, and mechanical load and any other components. Yes, so major components we have to define, and then we can say now we have to define the subsystem, correct? Establish the assumption. Yes, so we have to establish the assumption. So this assumption may be the this could involve the neglecting certain factor or assumes the specific characteristic to make the model more manageable. Maybe the you can consider the temperature, maybe the weather condition, anything, okay, and maybe the you can consider the air gap, okay. So any assumption you can consider. Development of the electrical model, yes. So typical model include the equation of the governing voltage, current, power, okay. So we have to develop the mathematical model. Same mechanical model, okay. So this include the modeling inertia, friction, any external mechanical load. So whatever mechanical parameter is there, so we have to develop the mechanical model. Then fifth one, that is a combine the electrical and mechanical model. Okay, so now we have to combine the mechanical plus electrical model, and then we have to make the simple electromechanical model. And electromechanical model is nothing but your model, your motor, correct? And then sixth one included the control system. Yes, now we have to control our motor, so we can say the response time, feedback loop, and any other relevant control parameter. Suppose you want to control the temperature, suppose you want to control the friction, anything. Suppose you want to control the movement, that is a theta, okay, that is a something like we can say robotics application, okay. Suppose you want to control the only robot arm, that is a 30-degree, 60-degree, again 30-degree. So anything you want to control, correct? So there is a control system part. Yes, then validation and parameterization, okay. So we have to validate the our model, okay. So whatever parameter you consider, whatever parameter you assume, so we have to validate by our experimental setup, correct? So how we can validate? By experimental setup, otherwise the any benchmark, correct? So suppose we can say ABB is a standard company to design the motor, correct, design the drives. So maybe you can consider the ABB as a benchmark. Otherwise, maybe the any experimental data is a benchmark, and then you validate your data. Correct. So suppose we are newly designed any control algorithm. Correct. So how we can say my control algorithm is a very good. Correct. So we have to compare our control algorithm with any benchmark, otherwise any well-developed experimental data. And then we can say, yes, my proposed algorithm, my proposed motor, it is a very good compared to other one, correct? Non-linearity means consider the incorporating non-linearity. Example, saturation effect. Yes, we can say now my transformer is a saturate, correct? Maybe your motor is saturated, then what we can do, correct? And the advanced feature, that is a sensorless control. Sensorless control, that is our fifth unit, and that I will discuss in Nepal. That is a physical class, and this is a very interesting topic, that is a sensorless control. Maybe the barrister covered the sensorless control, but only I think 8 and 9 student in the class, because that is an elective subject. But no issue. I will cover the sensorless control part for the motor, correct? Dynamic braking, okay. So any non-linearity component you can consider for the dynamic model. Yes, then simulation. You know very well about the simulation. There is a MATLAB, yeah, PLECS. So this is a similar to the MATLAB. Okay, so various softwares are available in the market. So maybe you can choose any software, but normally people use the MATLAB Simulink. Okay, and they are comfortable with the MATLAB Simulink. So that's why people use the MATLAB Simulink. But suppose you are comfortable with any other simulation tool, then you can use it. Okay. Sensitivity analysis. Yes, we have to analysis the sensitivity. Okay, suppose you increase the small parameter, maybe you can suppose increase the only 5% of the supply voltage, then what is the effect on the system, correct? So understand the how change in the different parameter affect, correct? So suppose you increase the temperature, so not temperature, suppose you increase the voltage, current, speed, then what is the effect on the flux? So that is a sensitive parameter analysis. And finally, there is a documentation. Okay. So including the equation, assumption, and the parameter value. Okay. So this documentation is crucial for the future analysis. So suppose after 6 months, after the 1 year, after the 5 years, you want to analysis again same model. So this document is will helpful. Okay. Yeah. So any confusion for the dynamic model for the electric drives? Yes. Any confusion? Okay. Yes, simulation tools to check the performance of the electric drives. Okay. So this is the simple and why we are doing the simulation tool, correct? You already performed the many experiment in the MATLAB Simulink. And last year also I asked the question in the Viva, why we have to do the simulation, correct? Is it possible we can directly go with the experiment, correct? So in the last semester, all of you told the correct answer. So because we have to save the time, we have to save the money. So that's why whatever you want that we can do in the simulation, correct? But that is not possible in the physical mode, correct? Suppose you want to change some voltage in the physical mode in practical application from 230 to maybe the 440 volt. Suppose you directly give 440 volt to your physical motor, so maybe you don't know what happened. Maybe the fire hazard, maybe the overspeed, yeah, maybe the overcurrent. But same thing, suppose you give in the simulation part, correct? So nothing will happen, correct? Only happen is your response will change, correct? But there is no losses, correct? But in the case of physical, maybe the damage is happen, correct? Maybe the damage, maybe the motor damage, yeah, maybe the fault happens, anything happen. That's why we have to use the simulation before going to the any product design, correct? So several simulation tools are widely used in studying the performance of the electrical drives. So it is not for only electrical drives, maybe the power system, yeah, any application. Okay. So suppose you implement the power network, maybe the 11 kV substation you want to implement. So we are not going to directly implement the 11 kV substation in the practical, correct? First, we have to design the 11 kV substation in the any simulation component, any simulation tool, maybe the PS card, maybe the SCADA, yeah, any software, correct? XYZ software. Once we are satisfied with the result, then we are going to implement in the physical mode, correct? So we know that MATLAB Simulink, PScheme, PSIM, LabVIEW, ANSYS Maxwell, PS Card. Okay, so many simulation tools are available in the market to implement our control our proposed system. Correct. So, but most of the people know about the MATLAB Simulink. Yes, few of the working on the PScheme, LabVIEW, ANSYS Maxwell, PSCAD. Okay, so many softwares are available. Yes. So type of the duty cycle. Okay. So type of the duty
So
cycle.
that PSIM full form, sir.
PSIM.
Yes,
PSIM
sir.
full form. Uh, I think PC full form is a power simulation. Just 1 minute. Just 1 minute. PSIM full form power
Okay, sir.
simulation.
When we have to use that, sir? PSIM.
PSIM for the power system. Suppose you are working on the power system and you want to design the maybe the 50-kilometer long transmission line, correct? So then we can mostly PSIM used for the power system engineering. That PSIM is mostly used for the power system. Just 1 minute. PSIM full form. Uh, just 1 minute. Yes, PSIM is a electronic circuit simulation. Okay, but full form I don't know. So where is the written full form? Full form I don't know. Yeah, full form I don't know.
Yes, sir. Maybe hardware or software, sir. That is simulation. I
Yeah,
guess.
PSIM is a software. It is not hardware. It is a software.
Yes, so
So
software also
MATLAB is software. PSIM is software.
some are hardware simulation related,
Yeah.
like Proteus is there. So is it a hardware or software related?
So this PSIM is a software related.
Like MATLAB? No.
Yes. Yes. So this all are is a only software. PSIM, MATLAB is software. PSIM is also software. LabVIEW is also software. You heard about LabVIEW?
No, sir. No, sir. Maybe also no.
LabVIEW is also software. ANSYS is also software. Mostly ANSYS we use for the finite element. Finite element. And we use the ANSYS to design our motor. To design the motor, we can use the ANSYS. And ANSYS is work based on the finite element method. Finite element method. Correct? So that is the ANSYS. And PSCAD again for the power system. PSCAD full form. Just 1 minute.
Our
PSCAD.
system computer aided design, I think, sir. Maybe.
Just 1 minute. I think so. Power system
So,
computer aided design.
so
Yes.
this finite element method, I have encountered this several times. What this actually means, sir? This finite element method.
Yeah, finite element method means suppose this is your just 1 minute. Yeah, finite element method is what? Suppose this is your stator, correct? I am saying this is your stator, correct? And we have a slot, correct? Here is one slot. Here is another slot. Here is another slot, and here is another slot. And we have a winding, correct? Every slot have a winding, and every slot is connected to the each other, correct? Something like that, correct? So this is simple. We can say stator, and stator have a stator winding. So we can say this is a stator winding. So what is the meaning of finite element method? Finite element method. What we are doing in finite element method, we have to analysis each and every component with a minimum distance. Okay, suppose area of this stator core, it is maybe the 10 centimeter diameter. Okay, diameter is a 10 centimeter of this stator core, correct? Area of this stator core is 10 centimeter diameter. And suppose you want to analysis, you want to see the how current is distributed over the 10 centimeter diameter. Otherwise, suppose you want to analysis the how temperature increase to the 10 centimeter diameter, correct? For the finite element is what finite element will do. Just 1 minute. Yes, I want to change the color. Yes, finite element what do? So finite element, so we have divide the this component into small section. So we can divide the stator part in the small section. This small section, and then we we analysis each and every part. Then we analysis each and every part. Suppose this is the first part, second part, third part, fourth part. So every part we can analysis, and then we can say, suppose you increase the speed, suppose you increase the load, then it will create this much effect in the stator winding. So that is nothing but your finite element method. So in the finite element method, we have to take the small section, very small section, and then we can analysis. And then we can say it is a finite element method. And that actually we are doing in the ANSYS software. Got it?
Yes, sir. Okay, sir.
Yeah. And that is a finite element method. So most of the that design engineer, they are use the finite element method. So see the behavior of the each and every component, correct? In the small sector, otherwise small portion, correct? Yes. Yeah. Uh, Only I will take the 15 to 20 minutes now. Type of duty cycle. Okay. So type of duty cycle is important. And what is a duty cycle? Any idea? Anybody? Any idea? Duty cycle? Yes, Asis. Any idea? What is a duty cycle?
Sir, how long we turn on and turn off?
Yeah, how long we turn on and turn off, correct? So how we can suppose you want to turn on the motor, maybe the 10 hours, correct? And then maybe that rest time is maybe the 1 hour, correct? So how long we can turn on and turn off? And suppose you want to continue operate, that is a 24 into 7, then what is the effect of the temperature, correct? So continue you are apply the current to the motor, and motor have a winding, correct? So it will continue consume the current, correct? So it will continue draw the current, so it will create the, it will generate the heat, that is a I square R, correct? So it will damage the some part, maybe the damage the motor, yeah, maybe the fault, yeah, something else. Okay, so we have to see the duty cycle, how long motor will operate. That's the on and off time period, and that is nothing but duty cycle. So nowadays, every application electric motor are used and control them electrical drives are employed. Correct. So simple. Every application we have to use the electric motor. Correct. So, but operating time for the all the motor is not same. Correct. Operating time for the every motor is not same. Maybe the some motor is operate for the maybe the 1 hour. Maybe the some motor is operate for the 2 hour. Maybe the some motor 24 into 7. Correct. But some of the motor run all the time, and some of the motor run for the shorter time than the rest time, correct? Maybe the some motor is operate only 1 hour, and rest time is maybe the 23 hours, correct? But maybe the some motor is operate 23 hours and rest time is only 1 hour. Okay, so how we can decide? So which motor is operate maybe the 23 hours, yeah, 24 into 7 hours, correct? That we can decide by the duty cycle. So depending on the concept of the motor duty cycle is introduced, and on the basis of the duty cycle of the motor can be divided into 8 category, correct? So depending on the motor cycle, the duty cycle, we can say now we can operate our motor on this range, maybe the 1 hour, 2 hour, 3 hour. Okay. Yes. So that 8 duty cycle is, first one is a continuous duty cycle, second one is a short time duty cycle, third one is an intermediate periodic duty cycle, fourth one there is an intermediate periodic duty with starting. Okay. So fourth one is an intermediate periodic duty with starting. Fifth one is an intermediate periodic duty with starting and breaking. Sixth one, there is a continuous duty with intermediate periodic loading. Okay, now is loading is a periodic. Continuous duty with starting and breaking. Okay, so continuous duty with starting and breaking, and continuous duty with a periodic speed changing. Okay, so there is one S1, S2. So we can say this is your S1, this is your S2, this is your S3, S4, S5, S6, S7, and S8. Yeah. So most of the time that standard designer, that standard industry, they mention S1 type motor, S2 type motor, S3 type motors. And this standard is as per the IEEE ISO. Okay. So that S1, S2, S3, they define S1 indicate that is a continuous duty cycle. And on the nameplate, they are mentioning this is the continuous duty cycle motor or short time duty cycle motor, correct? And they are mentioning the S1 otherwise or ISE, ISE standard. ISE standard, maybe the ISE 441, maybe the ISE 412, that standard, correct? So I am not sure though there is a 441, yeah, what, but there is a standards, correct? So they are mentioning on the nameplate of the motor. So customer know, so this standard, so we have to operate our motor. There is a maybe the short time duty cycle, continuous duty cycle, yeah, which type of duty cycle, correct? So we have a total 8 type of duty cycle. Okay. So total is maybe the 10 type, yeah, 11 type, but most important is only 6 duty cycle. Most important is up to 6. There is a continuous duty with intermediate periodic loading. 7th and 8th is not important. Only important is a 1, 2, 3, 4, 5, 6. Okay.
Actually, sir,
Yes.
sir, can you draw a waveform of on the right side, sir, of each? For example,
Yeah.
continuous duty, always on, short time duty, intermittent period duty. How to differentiate them?
Yes. 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 I will explain in the next slide. Yes. Yeah. So continuous duty cycle. This duty denote the motor is running long enough and electric motor temperature reach the steady state value. Okay, because continuous duty cycle, it means you continue operate your motor, correct? 24 into 7 you can operate your motor, correct? Then we can say it is a continuous duty cycle, correct? These motor are used in the paper mills drives, compressor or conveyor belt. Okay, so wherever your motor is continue operate, there is a 24 into 7, then we can say it is a continuous duty cycle. So waveform, you can see on the y-axis there is a load torque, and on the x-axis there is a time. Okay, in time maybe then the second, correct? Yeah, maybe the time in the hours, correct? So because this is a continuous duty cycle, so we can say time in the hours, correct? So you can see that load is a constant, correct? So in the paper mills, compressor, and the conveyor belt, everywhere load is a constant. We are not changing the load, correct? So maybe then we can say load is a constant, maybe, and this load is maybe the 10 Newton into meter. Okay, and we are not changing the load with respect to time, correct? So load is a constant, correct? And we are continue to operate this motor 24 into 7, correct? So we can say what is the effect on the temperature, yeah, what is the effect on the theta, correct? Okay, so on the y-axis there is a theta. Okay, so we can say slowly temperature is increasing, and then finally it is a reach to steady state value, because now motor is not fluctuating the load, correct? Once the motor fluctuates the load, then suddenly current is draw, correct? Because torque is directly proportional to the current, correct? So suddenly load change, then suddenly current change, and suddenly current change, then it means it is your temperature is continuing increasing, correct? So this is the waveform for the continuous duty cycle. Okay. Yes, and now next one, that is your short time duty cycle. Short time duty cycle means you have to operate your motor in the short duration, maybe the 1 hour, yeah, 2 hour, yeah, maybe the 3 hour. Okay, that depend on the application. So that name suggests that is a short time duty cycle. In this motor, the time of the operation is a very low. Okay, so operation time is a very low, maybe the 1 hour, maybe the 10 second. That depend on the type of the load and depend on the size of the motor. And the heating time is much lower than the cooling time. Okay, so heating time is much lower than the cooling time. So the motor cooks off to ambient temperature before the operating again. Okay, so what is the application for this short time duty cycle? These motor are used in the crane drive. Okay, so we can say in the trick crane, correct? In the crane, so we have to we have to lift the weight, correct, for the short time period, and after that there is a rest. Okay, so crane drive for the house load application. Yeah, you can consider your mixture, correct? In the house load kitchen, we use the mixture, correct? So in the mixture, we can say we can operate our motor maybe the 1 minute, yeah, 2 minutes, and then it's a rest time period, correct? So it is a short time duty cycle. So you can see on the y-axis there is a load torque. Yes, for the sometime we can give the load. Maybe here is a 5 Newton meter, and this time period may be the 5 second. Yeah, not 5 second. Maybe the we can consider 5 minute. Okay, and after that there is a rest. So you can see then it is a again that is a zero load. Okay, Newton into meter, correct? And maybe this time period is maybe the 5 minute. Okay, correct? So there is a short time duty cycle, and then you can see the temperature, it is a increase, and once the your motor stop, then we already know temperature is we cannot continue, we cannot suddenly increase or decrease the temperature, correct? So it will take some time to reach to zero temperature, correct? So yes,
So that
temperature we cannot
so
suddenly
that
change. Yeah.
so the temperature while operating, sir, is increasing non-linearly, and when turn off it is decreasing very linearly. How, sir? It is same motor, same coil.
So your question is temperature increase the linearly and decreasing.
No, sir, increasing non-linearly, like it is about to saturate after some time, but
Uh-huh.
decreasing time it is decreasing straight line, linearly.
Yeah. Yeah. So your motor is operating, correct? You start your motor, correct? Correct. So you start your motor and we have a copper wire, correct? So once you pass the current to copper wire, so we can say we suddenly not increase the temperature. Any material, not the copper wire, maybe you can say aluminum, yeah, maybe iron, yeah, any material. So suppose you want to increase the temperature of the any material. So the temperature is increased slowly. It is not suddenly increase the temperature for any material. So that's why once you start your motor, so it will not suddenly increase the temperature. It is not like that, increase the suddenly temperature. It will take some time to increase the temperature, correct? So that's why it is your line is a slowly increase the temperature. But once it reach to the maximum, correct? So we can say now your motor, you want to stop your motor, correct? So this line, now you are stopping your motor, correct? So then suddenly you drop out this temperature. So you can see you shut down your motor is here, but your temperature is not continue here, something like that. It will take some time again to uh, reach the cool down, correct? Otherwise what happen? Otherwise this graph is something like that. So this is your increasing, and you stop the motor is here, so your temperature is here. Graph is something like that. This is state line, something like that. Not this one, not this one. But we know that temperature is not continue increasing, suddenly increase and suddenly decrease, correct? Once the temperature is high, then it will take some time to cool down. That's why this plot is here. This plot is here, not here, not here. Otherwise you stop the motor is here, correct? So suddenly, immediately your temperature come down. But by nature, we cannot reduce the temperature immediately, correct? It will take some time. That's why slope is from here to here. Got it, Asis?
Yes, sir. Yes, sir.
Yeah. Yeah. So this is first one is a continuous duty cycle. So we have to operate the motor continuous. Okay. Second one is a short time. So we can say for the minimum time we can operate the motor, and the remaining time that is a rest time. Okay. Yes. Third one, that is an intermediate periodic duty cycle. So first, second, and third is important. Okay. And remaining three, that is just dependent to each other. Correct. So third one, that is an intermediate periodic duty cycle. Intermediate periodic duty cycle, it means maybe the 0 to 5 minutes you can operate your motor, then 6 to 10 minutes there is a rest time, there is an off time period, and then again 15 to 20 minutes again that is operating, correct? So we can say turn on, turn off, turn on, and turn off. Okay, so this type of operation. Okay, and where we can use this operation, practical application, this is seen at the press and drilling machine. Okay, so that is a drilling machine, correct? So suppose you want to drill in the wall, correct? Suppose you want to do the hole in the wall, correct? So for the any wall you want to drill, correct? So we have to use the drilling machine to for the holing, correct? So sometime maybe for the once the drilling once the hole is completed, then your drilling machine is turned off. And suppose your hole is not sufficient, then again you can do the drill, correct? So we can say yes, for the 0 to 1 minute maybe the your motor is operating, and after that maybe the 1 to 2 minutes, yeah, 1 to 3 second 1 to 3 minute, maybe that your motor is not operating. So we can say that is an intermediate periodic duty cycle, correct? On off, on off. So we can say here is a on, here is a off, on, off. And same thing you can see here also. Yes, Asis, you can observe here also. So off time period, on time period. So same thing is here happen. So we cannot suddenly increase the temperature and suddenly decrease the temperature. It will take some time, correct? Because temperature is dependent on your material property, and we cannot suddenly increase and decrease the temperature. Okay. So this is your intermediate periodic duty cycle. Okay. So maybe here is torque, maybe the 5 Newton meter, 5 Newton meter, okay? And then is a 0, okay? Yes. Intermediate periodic duty with the starting, okay? So in the starting, intermediate periodic duty with the starting, okay? So in this type of duty, there is a period of the starting which cannot be ignored, and there is a heat losses at that time, okay? Yes, so we can say we start the motor, correct? But we cannot stop the motor. But we can say now we don't have a load, correct? But still motor is started, correct? Motor is running, but there is a without load. Okay, so we can say yes, now motor is started. So you can say simple, your vehicle, correct? So we are driving our vehicle, okay, and maybe on the road you can drive continue your vehicle, correct? And maybe there is a red signal, okay, in the signal light is there, correct? So you can just stop, but your engine is on, correct? Still your engine is on, correct? So we can say yes, my engine is on, but there is a no load, correct? Yes, you are sitting on the vehicle, but we can say you are not running on the vehicle, you are not running on the way on the road, correct? So we can say intermediate periodic duty with the starting, correct? After that there is the running period and the rest period which are not adequate to attain the steady state temperature. Okay, so practical application, as I said, this motor duty cycle is widely used in the metal cutting and drilling tools, driving or mine hoist, etc. Okay, maybe the metal cutting application, yeah, driving, drilling tool drives, otherwise the mine hoist. Okay, so you can see here is a starting. Okay, then yes, reduce the weight. Okay, so there is a rest time, and after finally there is a rest time. Okay, in the
Sir,
metal
sir,
cutting
sir,
application,
sir, I
yes,
think that running means that small portion that after starting.
yes. So here is your full loaded. Here is a loaded. So you can see in the metal cutting application, suppose you have a metal plate, correct? So this is your plate, and you want to cut this metal plate. You want to cut this metal plate, correct? So we can use the maybe the any device to cut this metal plate, correct? So initially we can say yes, to cut this metal we have to give the more current, correct? So yes, that is a starting, we have to give the more torque, correct? And then once the metal is cutting, then we can say we are not only turn off the power supply for our drilling machine, correct? Yeah, maybe we can say the cutting tools, correct? So we can say this is a rest time. Okay, but this is not the full rest time. Still your motor is rotating, correct? Once this fully meter is cutting, then we can say now is a rest time, correct? Now we can say this is a rest time, so this is a off time, and this is a on time. So yes, we
So,
can say
sir,
this is a starting
I think
condition, that is a running.
that is cycle repeat, sir. The second graph is the repeat of the same cycle.
Yeah,
That is
second is the
small
same cycle.
ladder. That is small ladder. I think portion is running portion, sir. Where
So this one,
no, sir, above one.
this one.
Yes, sir. That is small portion. That is running part. I think.
So this return is starting, correct?
So in starting, it draw high current, or therefore torque is high, and after in
Uh-huh.
running condition, with torque is lower, current is also lower, so heating is lower in that case.
Mm-hmm.
And again, machine is after that turned off, and cycle
Mm-hmm.
is repeated. I
Mm-hmm.
think it is that way, sir.
Just 1 minute. Just 1 minute. So running period and the rest period, that are the adequate to attend. Okay. So I have to check, and most probability this is a running, not the starting. Most probability this is a running. So I will check this one. So this one is starting, yeah, running, because yes, you are correct. So this cycle is a
Because sir,
repeating.
if you just start, then why you turn off without running? Let us say you start, then you let it run for a while. You start,
Uh,
then turn off, then again run again next time.
just repeat. Just repeat.
For example, if you start, then without letting it to run, why you turn it off? Why you allow it to rest? That is, so I think it is first starting and then running and then after rest.
No, then starting, okay. And why then? Suppose you start at 10 Newton meter, correct? Okay. Suppose you start at 10 Newton meter load torque, okay, and then again you can decrease your load torque. So maybe this load torque maybe the 7 Newton
Yes,
meter.
sir. Because some one machine are there, the starting torque we have studied that static friction is high, so it draws high
Okay,
inverse
okay,
current
okay.
to
So you
start.
are saying that starting torque is a very high, correct?
Yes, sir. Yes, sir.
And then after the starting, maybe the 100% starting, then maybe it is a reduce the starting torque,
Yes,
correct?
sir. Then it is
So you are
easier to
saying
run the machine.
maybe the yes, but yes, maybe that is a correct. So once the motor is started, then it is a yes. I think yeah, yes. But I will check that thing. Yeah, then is that, then we can say yes. In the case of the induction, in the case of the DC series motor, we see the DC series motor we cannot operate the like without load, correct? So it because that is a high starting torque. Yeah, same we can think lah. Yeah, I will check that thing. So starting and running thing. Yes. Okay. So that is a metal cutting application, drilling tools, and everywhere we can use the types of the that is a intermediate duty cycle, intermediate period duty cycle with the starting. Okay. Yes. Yes, Asis also send me this question. Huh? That is a starting and running. That is a fourth duty cycle. So maybe you can write only intermediate periodic duty cycle, a duty with the starting, and write in the bracket that is a waveform. Okay. So just send me this query also. So I will just verify. Okay. Yes. Here is also same. That is an intermediate periodic duty with the starting and the breaking. Okay, intermediate periodic duty with the starting and the breaking. Okay, so here is starting as well as the breaking. So breaking, there is a, again there is a negative zone. Okay, and here is also a negative zone. Okay, so but here is same repeating cycle. Okay, so we can say this is a starting and running, same as the previous slide. So we can say initially starting torque is high, and once the motor is reached to the maximum speed, then it will come down. Correct? So we can say yes. So as of now, we can assume that is a starting torque is high, and then after some time it is a reduced the torque, and then we can say now is a running condition. Okay. And braking operation, yes, we can know braking is your negative zone. Correct? So that is a braking operation. Okay. Yes. Yes, 6, 7, and 8. It is a most not important. Important is only one. Most important is a first. There is a continuous duty cycle, short time duty cycle, intermediate periodic duty cycle, intermediate periodic duty with starting, and intermediate period duty with starting and breaking. So these 5 duty cycles is
Sir,
most
sir,
important.
here
Yes.
in here second bullet, if you read, sir, it is clear. I think the doubt is clear, sir.
Just a minute. So the corresponding the period is starting period, operating period, breaking period, and the resting period. But all the period are the too short and attain the respective steady state temperature.
So that all ladder step is starting, operating, braking, and resting. I think so.
So the corresponding the period are the starting period, operating period. To short and attain the respective steady state. Done. Yes. Yes. Done. So this is yes. This ladder. Yes. Done. Yeah. Yes. So continuous duty with the intermediate periodic loading. Okay, so no waveform here. But this 6 1, 7th, and 8 1 is not important. Continuous duty with the starting and breaking. Okay. So sometimes starting and after that breaking. So we can say steel mill also example. Continuous duty with the periodic speed change. Yes. So periodic speed change, that is a new thing. In this type of motor duty cycle, there are the different running period of the different load and the speed, but there is a no rest period, and the all the period are the too short to attain the steady state temperature. Okay, so there is a periodic speed change. Okay. Yes. So so this one the type of the duty, and duty is the most important for your EST paper, not for the MST. Yes, now I am talking. Yes, so this one is the final one. So today's point from the class. So there is a space vector PWM, difference between the VSI and CSI, and the cube law, and then development of the dynamic model and simulation tool, and finally types of the duty cycle. Yes. So from the today's class, how many question? Yes, Asis. How many question is pending from the today's class?
No, sir, all clear, sir. I think all.
All clear? Yeah. I think one is one you have a question that is power factor, correct? From the previous class. Correct? I think
Yes,
so.
sir. Yes, sir.
So just message me, huh? Just message me. So I will work out on that and get back to you. Okay? Just message me. Yeah. So this all are from the today's class, and thank you so much. Now, yes, 1 minute. Uh,
Excuse me, sir. I
job
have a
look-
small question.
yes, yes, yes.
Sir, in last class I was absent due to my health issues. So I need to make me clear about the coming exam.
Mm-hmm.
So we need to prepare lecture up to till date for coming exam, or there is some limited lecture.
Not for today's class lecture. Not
So
today.
up to last class.
Yes, up to last class.
Uh, so we have another assessment this Wednesday,
Mm-hmm.
modeling and